Welcome to Data Skeptic. Our mini episodes are gentle introductions to concepts related to artificial intelligence. These short discussions are meant to serve as a primer for the topic. Learn more by reading our show notes at dataskeptic.com.
All right, Linda, our topic for today is first-order logic. And let's just start with the logic part. What do you think of when someone says logic?
I'm glad you asked because I looked it up.
Okay.
And it says, reasoning conducted or assessed according to strict principles of validity.
Yes.
So there's principles of validity.
Mm-hmm.
So that probably would be up for debate if we were to explore further.
Yeah, so logic is a set of rules and methods for deriving new facts and information and proving theorems and stuff like that. And it needs to be consistent and
validity.
Have validity too. Although I think that's probably the same thing as consistent. Well, no, it also means that any conclusion you draw, if you follow the logical rules, that it is true. In other words, you wouldn't be able to prove something is false and have it be true.
It didn't say the word true. It said validity. Logic doesn't mean it's true.
Well, I'm getting a little bit more mathematical, but valid is maybe a property of the proof, that it follows all the methods, and any proof arrives at some truth. So what most people think of when you talk about logic is prepositional logic. So that's like saying that, Linda lives in Los Angeles. Kyle lives in Los Angeles.
Therefore, Yoshi lives in Los Angeles.
Yeah, exactly. So you get kind of like structures like that, where it's like A and B, A implies B, this kind of stuff. Maybe you remember modus ponens or modus tollens, those two things, or De Morgan's laws, if you ever took a logic course.
Never heard of that.
All right, those are just names of how you can kind of transform the arguments and stuff like that. So prepositional logic is when you just have kind of variables to represent ideas, and you talk about the relationships. The classic one is Socrates is a man, all men are mortal, therefore Socrates is mortal. That's the kind of the plain vanilla basics of logic. You have the prepositions, and then you have the relationships between them, what they imply about each other, their causal relationships, stuff like that. Now, first-order logic adds in some new ideas. The key ideas are the quantifiers. So the statements, there exists and for all. Do those names kind of intuitively tell you what they do?
Quantifiers. I don't know what quantifiers means. What does that mean?
Well, I gave you the two, so let's just do the first one. There exists. So I could say, there exists a bird such that that bird lives with Kyle and Linda, and that bird is a lilac-crowned Amazon. And that would be a true statement, right? Because such a bird does exist.
Yes, we have Yoshi.
Now, how about the statement, for all birds, the bird lives with Kyle and Linda?
For all birds?
Yeah.
The bird? Well, I'm confused because it says for all birds,
right,
bird. So I'm not sure what it's talking about.
Oh, I see what you're saying. So let me try it again linguistically. It would be for all birds, each one of them lives with Kyle and Linda.
Well, I mean, it's vague, but the point is it's implying that there's multiple birds and we only have one bird. So it's false only because we only have one bird that lives with us.
In what way do you find it vague?
Well, it says for all birds. I don't know what that means. Okay. For all birds. So for all birds of what? In LA?
Well, it just means for all. It means all of them. Those are the two quantifiers. So you might have something more specific. You could say, for all birds such that the bird lives in LA, they also then live with Kyle and Linda.
I'm confused. Say it again. What's the statement?
Well, let's maybe go with a true one. For all hosts of Data Skeptic, their mailing address is in Los Angeles.
Hosts.
Mm-hmm,
well, it depends if you think we're a host, but yeah, we live in Los Angeles.
Yeah.
True.
And that's because for every single host that there is, just you and I at this time, the statement holds true.
Why do you start the sentence with for all? I mean, because usually when you say for all, I don't know, it's just an odd statement. Why wouldn't you just say all? Because grammatically, for all is something awkward about that statement.
Maybe to the English grammar, but the mathematical grammar of first-order logic, this is how you do it.
So you start every sentence with for all?
Do you start every first-order logic statement with a quantifier? Not necessarily, but the majority of them, since first-order logic is interesting because of these two quantifiers, you generally start with either there exists or for all. In fact, you don't even write those words out. They're special symbols. You write a backwards E for there exists, and you write an upside-down A to say for all.
What's the difference between there exists and for all?
You're going to talk about some set, like the set of all birds, or the set of all cities, or the set of all podcasters. And then if you say there exists, that means that if you look really hard, you'll find at least one example in the whole set. Similarly, you could say for all millionaires, there exists one who is just lucky. And certainly that's true, right? Somebody got rich by chance, but many of the people did it by skill too. So you wouldn't say for all millionaires, they're lucky.
What language was this come upon? Because I've just never heard anyone say for all, period. I've never heard anyone say that phrase.
Well, it's pretty standard in first order logic.
Okay.
So
where do we go from here?
Well, we'll talk a little bit about how it fits in with AI once we've got the basic ideas down. So we've got these two quantifiers, and then we talk about different functions. So when you read these things, usually it'll read like, they'll use the phrase is a, so like is a bird, is a car. So for all x such that x is a bird, that kind of stuff. Now, why is this interesting in AI? Well, let's first start with why is it interesting in general. So it's interesting because it's a confined logical statement. There's limits to what you can describe with first-order logic. Otherwise, there'd be no such thing as second-order logic and no other types of logic. It's better than just prepositional logic where you say, A and B implies C and that kind of stuff. You get this extra little mechanism, this quantifier where you can talk about stuff that, one example exists or all of the examples hold the same property. And if you don't go further than that, you don't talk about the functions themselves or the sets too broadly, then you can prove that all your first order logic stuff is complete and sound and valid and all those good properties. Because the dirty secret underlying logic is something called an incompleteness proof. And there's lots of these, but the core one was by a guy named Kurt Gödel, Gödel's incompleteness theorem, which says something to the effect that there is no mathematical system which is consistent and can prove all true statements. I'd like to thank this week's sponsor, Brilliant.org, for their support of Data Skeptic. And in particular, given our topic for today of first-order logic, I want to recommend Brilliant's course on logic. This course starts with a love of puzzles and building up some truly mind-bending challenges. It covers liar and truth-teller riddles, logical fallacies, machine logic, and even some strategic game theory. By the end of the course, you'll be able to solve problems involving and not and XOR gates, as well as using the symbolic language of logic to understand fun riddles. This course is a great instructional tool for learning logic, which is really fun along the way. I just started playing Advanced Knights and Knaves, which is the last stage in the logic course. It's this fun little game where you apply logic to solve these challenges, all in your browser. Guys, you got to check this out. Brilliant.org/dataskeptic. One more time, that's brilliant.org/dataskeptic.
There is no mathematical system that is consistent and can prove what?
All true statements.
All true statements. All true statements. Well, I don't know. Just that alone, if you're trying to make a statement and you lump in all true statements, it's most likely false.
Well, that's a bit heady and a topic for another podcast, I think. But the core idea here is because logic is, by proof, incomplete, sometimes we want to look at systems that are a little bit confined where you still get nice properties. For example, we talked about the halting problem previously, that you can't perfectly check a computer program to make sure it does its job. So you write a bunch of unit tests and you smoke test it and do all types of things to hopefully ensure that your software is good, but you can never absolutely prove it. However, under certain confined circumstances, you can say if we limit the way we write the software, we can guarantee this limited version is always going to work correctly. And the same is kind of true with first-order logic. It's very powerful, but it's limited. Now, that's what's interesting about first-order logic. Why is it interesting in the context of AI? Well, because a lot of people use it for what's called knowledge representation. So knowledge representation is how you kind of store information. So if you were trying to create a chatbot, let's say, and while you were talking to the chatbot, you say something like, the sky is blue. And if the chatbot wants to remember that and retain that information in some useful way, it might associate the property of being blue with the object of the sky.
Being blue with the sky. Mm-hmm. So what does that have to do with this topic?
So you might store that information in first-order logic.
How is that useful, though?
Because that is a way that now you formalize that information in logic. So maybe you can use it to do inference. So once you know that an object has certain properties, like if I said, hey, Yoshi is a bird, and you store that, then if you also know that for all birds, they have feathers, then you can draw an inference and say, well, I know Yoshi must have feathers.
Yes.
And you can draw those sort of things prepositionally, but now you can inference with this existential qualifier that there exists something, or for all, so you can assign properties to objects in a more robust way.
So do you use this on your job?
I have never had the pleasure of being able to implement first-order logic in any project I worked on, but I do know people that use it for knowledge representation when they're doing AI type stuff.
Do they type it out as words?
No, you build up a system that recognizes those entities. So like, let's say it was over text and I give you some statement. It would figure out, well, what are the objects in it? Like what people, places, things, what are the nouns basically? And then it would try and determine what are the relationships or information shared. That would be like an algorithm that would do that and store it in this first-order format. And then you'd have a database of first-order logic. And once you get your information into that system, then you can inference very efficiently.
So you have to train it to accept these statements?
Well, if you were going to use this for a chatbot, let's say, which is something I've toyed around with maybe using it on our chatbot, I would first have to break apart the sentence and figure out what the objects are.
Do you store it as words? Or is it something else?
Probably a little bit more formal of a system. You'd have some sort of data structure that holds it or some database table that you put it in. But it would most likely, you're going to use a lot of different like strings, so you're going to say is a bird or is a grocery store, and you'll have those relationships and those will be formally defined, but they'll be treated in a special way. So if you just store it as a string, you'd have to reprocess it every time. So probably you want to store it in a more efficient way.
So this is first order logic.
Yep.
So what's second order logic?
Second order logic would allow you to, for the major thing in my mind, I think if we looked up the definition, there'd be like 3 or 4 big bullets. But the one that matters to me is second order logic allows you to have quantities over functions. So a function is anything that takes as input one of the objects in the system and then returns some value, like true or false. So let's think of the function is a bird. If you give it the object Yoshi, it says, yeah, that's a bird. If you give it the object Linda, it says, no, this object is not a bird. So you can say, for all x is a bird kind of stuff, but you can't say for all is a functions. Like there does not exist a function that checks what species you are that also, you can't make a statement about the functions basically. It's hard to maybe understand what that is without getting a little deeper into logic though. But basically, first-order logic is just limited in that you can only make statements about the prepositions themselves.
So second order builds upon first order.
That's right.
Okay.
And I'm pretty sure it does not have those same properties I discussed where you can kind of make completeness statements about it. And that's why people like first-order logic. One of the reasons why I think first-order logic's not more popular is because as you construct it, you kind of have to impose your own schema on it. And like you said, we'd like to say for all birds has feathers is true, but there are little exceptions to it, And whenever you want to give kind of a rigorous definition of something, you generally find there's always some little outlier that's screwing you up. So the way you'd handle that, it's not a problem with first-order logic. You would just have to alter that function or the definition of a function to include either to look at some other property or to include something else or switch it to,
you may just think it's worth it to simplify it and it's not worth it to account for these.
That could be, yeah. Maybe, depending on what your application is, you would say as long as something is 99% true, we will call it a for all quantifier in our system, even though then you might derive some false statements.
Right. Might be good enough for whatever you're using it for.
Yeah, so if you're going to use first-order logic, you really have to kind of figure out what your application is and how to apply it. The one, like I said, that I've toyed with is using in our chatbot, where it would have to recognize what the entities are and then learn information from people. So that would be cool because it would be unstructured, but its knowledge might get a little sloppy, It might possess information but not know how to do the same inferences human beings would do.
Well, that's the point of a machine. It can't do human things.
Not yet. But, we've been talking about AI for months now. You should know by now.
But you just stated an obvious statement. It can't do what humans can do. Of course it can't.
No, that's not obvious at all. In fact, it's not true. There's nothing a human can do that a machine can't be built to do.
Well, I can't tell my phone to search for something, and it get me on the first try sometimes.
I didn't say there exists such a machine. I said that for all machines, there's no such limit.
Today, there's a limit, yes.
Not a theoretical limit. Maybe Homo sapiens have failed to figure out the ways to build the machine you're looking for, but there's nothing that prevents such a machine from existing.
Is there a theoretical limit to the human brain?
Depends on what you mean. Obviously, it's limited in capacity, so there's that, but do you mean like the creativity of the brain? Sure, yeah, computational complexity is the limit of human creativity. There are problems that are provably hard to solve, and there's no reason our brain would solve them efficiently.
Efficiently?
Yeah.
But it doesn't mean You said it's not solvable.
Well, yeah, I mean, for any solvable problem, a solution has to exist. And if you can write down the format of the solution and someone just makes a lucky guess, then yeah, they can always find the solution. The question is, if you can't make a lucky guess, you want to have an algorithm that finds the answer. Sometimes that's easy, sometimes it's hard, depending on the problem.
Well, we'll just have to agree to disagree on what machines are good for.
No, I think you need to go back and listen to this whole semester of Data Skeptic, and especially my talk from the Skeptical when I was up in Berkeley. When that comes out, it'll be our feature of the week, so sign up for our mailing list and you can see that. But I address exactly this question in my 40-minute presentation.
Well, for us listeners who just want the lowdown, what's your summary?
I just gave it, that there's no limit to what a machine in theory can do with regard to intelligence. We are intelligent machines, and there's no reason a mechanical built digital computer couldn't achieve the same thing.
So that's Kyle's summary. So go back and listen to it.
All right. Because, yeah, we know we're counting down here. This, I believe, is the last episode of our series in AI.
Well, time has flown.
So starting next week, we pick a brand new topic that's been totally top secret. You know what it is.
It's secret.
Yeah.
I dropped a hint if Kyle keeps the editing.
Yeah, that might get edited out, but we'll see. Anyway, join us next week for a whole new show. And thanks as always for joining me, Lindy.
Thank you for joining me, Kyle. Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.